Hey everyone, if you've got an exam on vision transformers coming up, then you are in exactly the right place. We're going to cut through all the complexity and just focus on the core concepts you absolutely need to know to ace it. So let's dive right in. You know, the entire field of vision transformers, or BEiTs as we call them, it really all boils down to this one single revolutionary question. Researchers were seeing this incredible success with transformer models in understanding language, reading sentences word by word, and they just asked, hey, what if we could do the same thing with images? Okay, here is our game plan for this review. We're going to start with that core revolutionary idea. Then we'll get into how VIDs actually see using something called patches. After that, we'll tackle their single biggest weakness, this data hunger challenge, and then cover the wave of innovations that solved it. From there, we'll look at the incredible segment anything model, and we'll wrap up with why any of this stuff matters in the real world. All right, section 1, the revolutionary idea. So for years and years, computer vision was totally dominated by convolutional neural networks, or CNNs. These things work by scanning images piece by piece. The huge idea behind VITs was to just throw that out and replace it with attention, which is a way for the model to see the entire image all at once. So, what is a vision transformer? The key definition for your exam is this. It's an architecture that takes the transformer model, the one that's so famous for understanding language, and it applies it directly to images. And how does it do that? Well, it breaks an image into a sequence of smaller pieces, or patches, and then it processes that sequence just like it would process a sequence of words in a sentence. So, how does this whole thing actually work in practice? Let's break down how a model that was designed for text learns to see something like a cat or a car. This is all about thinking in patches, not pixels. Okay, so the very first step is super important, but it's also surprisingly simple. The VIT takes a picture and just slices it up into a grid of smaller, non-overlapping patches. I want you to think of it like turning a photograph into a mosaic of tiny square tiles. Each of those tiles, usually 16 by 16 pixels, is then treated as a single unit, almost like a single word in that sentence we were talking about. Now, this right here is a classic exam question. Compare VITs and CNNs. A CNN, it works like an investigator with a magnifying glass, right? It scans these small sections looking for local features like edges and textures, and then it slowly builds up a bigger picture. A VIT, on the other hand, just takes a big step back. It looks at all the patches at the same time, and it uses its self-attention mechanism to figure out how every single patch relates to every other patch. It's getting the global perspective right from the start. To help make that idea of self-attention really stick in your head, just use this analogy. A VIT is like looking at a class photo. It doesn't just see one face, then the next one. No, it sees the entire group instantly. And it understands all the relationships. Who's the tall one in the back? Who's standing next to the teacher? Who's making a funny face? It gets the whole context in one single go. So this ability to see the whole context at once is pretty much the superpower of VITs. But, like any good origin story, this power came with a major weakness, a really critical challenge that you need to understand for your exam. They were incredibly hungry for data. This data hunger all comes down to a key concept called inductive bias. CNNs have this built in. Their design inherently assumes that pixels close to each other are related, which is a fantastic head start for understanding images. VITs, though, they have no such assumption. They start from a completely blank slate. They have to learn from scratch that a patch of a cat's ear is probably next to a patch of its head, and that requires millions of examples to learn something a CNN basically knows by design. And this chart right here illustrates the problem perfectly. When the early VITs were trained on a standard and pretty large dataset like ImageNet, which has about 1 million images, they actually did worse than established CNNs like ResNet. They just didn't have enough examples to learn those fundamental visual rules from the ground up. So the crucial point is this. How did they get past this weakness? Well, the answer was just an absolutely massive amount of data. It wasn't until VITs were pre-trained on these gigantic web-scale datasets, and we're talking 300 million images, that their true power was finally unlocked, and they finally started outperforming the best CNNs. Now, needing 300 million images isn't really practical for most applications, right? That data hunger challenge we just talked about is precisely why the next wave of research was so critical. The whole community got to work developing some really clever solutions to make VITs way more efficient. Here are 3 key innovations that you should definitely know. First up, DIT, which stands for Data Efficient Image Transformer. This one cleverly used an already trained CNN as a teacher to help the BEiT student learn much faster with way less data. Second, the Swin Transformer. This made that global attention mechanism more manageable by having the model focus on local windows of an image instead of the whole thing at once, which saves a ton of computation. And finally, DINO, which was a huge breakthrough in self-supervised learning. It figured out how to teach a BEiT to identify different objects in an image without needing any human-made labels at all.
Okay, so all of this foundational research, it really paved the way for one of the most exciting applications to come out of VIATs, the Segment Anything Model, or SAM. And this thing is a true game changer.
So what is SAM? Well, in short, it's a model that can cut out any object from an image with incredible precision. And the best part is, you don't need to be a data scientist to use it. It works based on simple, intuitive prompts from a user, which makes it a huge step towards truly flexible computer vision.
The process is just beautifully simple. First, the user gives it a hint. It could be a single click on an object, or maybe a box you draw around it. Second, SAM instantly figures out what object you're pointing to. And third, it generates a perfect pixel-level outline or a mask around that object. It's honestly like a magic wand for photo editing. Okay, so we've covered the theory, but for the exam and really for your future careers, it's so critical to understand why this technology actually matters. Let's connect all these technical ideas to their really exciting real-world applications.
The impact is already huge. In medical imaging, BEiTs can analyze scans and pinpoint tumors with a precision that helps doctors save lives. For self-driving cars, they are absolutely essential for segmenting everything on the road, pedestrians, other cars, traffic signs, which is obviously critical for safety. And for all of us, they're powering the next generation of creative tools, making things like advanced object selection and photo editing just easier than ever before. So that's your review of Vision Transformers. We started with a pretty simple question, and we ended up with models that can see and segment the world with just incredible flexibility. It leaves us with a final, thought-provoking question for the future. Now that our AI can segment anything, what will we teach it to?
If you found this helpful, hit subscribe and the bell so you never miss a video.